Hello, everyone, and welcome to our next exciting talk of the day. Next up, we have Yu Dong, and he is the Senior Staff Technical Product Manager at Cruise. And today his talk is entitled AI-Driven Development for Autonomous Vehicles. Please give a warm virtual welcome to Yu Dong. Okay, you can join us. And I'll be here. I'm just going to turn my video off, but I'll be here if you need anything, and have a great talk.
Thanks, Morgan. I'm going to share my screen.
Great.
Cool. Okay, hello everyone. My name is Yu Dong. You can call me Robert. I'm a senior staff technical product manager at Cruise. Today's topic is about AI-driven development for autonomous vehicles. I will start from a brief AI-driven development cycle introduction, followed by how Cruise is leveraging AI to build autonomous vehicles. So before I jump into details, let me introduce myself first. Academia-wise, I got my bachelor degree in China and went to Florida International University to get my engineering PhD. After wearing engineering hats for several years, I became more and more interested in how technology, especially for AI, can benefit people's life and business. So I went to Berkeley Haas Business School for my MBA. Professional-wise, I started my career at Cisco as a software engineer and later become engineer manager. At Haas Business School, I was exposed to a lot of product and entrepreneurship experiences. So I switched to product role in Facebook with focus on AI relevant products. Like FB Learner, which is an AI platform used by a lot of hundreds of internal Facebook teams, and Marketplace Growth, where we applied AI machine learning to grow 1 billion user ecosystem. Currently, I serve as a product lead in Cruise with focus on perception-related products. Okay, let's jump into today's topic, AI-driven development. So what is AI-driven development? From my perspective, the development is normally composed of a multi-layer technology stack, like the one I'm showing in the slides. The lowest layer, which is a cloud infrastructure layer, which is similar to all other traditional software architectures. We have servers, data storage, and network. The middle layer, which is AI framework layer, which is a core AI layer, and includes different AI frameworks like TensorFlow and PyTorch, before we have Caffe too. At this layer, various machine learning architecture, network layers, and operators are defined and developed here. The up layer, which is AI workflow layer, which involves various AI machine learning workflows development, management, and deployment. From my own perspective, the AI workflow layer is a composition of AI framework layer and focus on specific problems we're trying to solve through AI in the real life. And also most AI machine learning engineers and data scientists are working on this layer, AI workflow layer. So at AI workflow layer, what's this horizontal view of AI development life cycle? Normally, we have 6 stages: problem definition, data injection or data processing, feature engineering, model training, model evaluation, and deployment. I will discuss in details about all those stages in the next few slides. So, problem definition. As a PM, I always start from the problem definition and the KPI to measure the progress. Meanwhile, there's no point to using AI machine learning just for the sake of doing something cool. From my own perspective, AI machine learning might not be implemented if the problem, first one, can be solved by simple rules or heuristic. We don't need AI here. Or the problem does not adapt to new data, which means if you give 10x 100 data, you don't see any improvement. In this case, AI is not effective here. The last one, if you need fully 100% interpretability, AI may not be a good role here because sometimes even the baseline, you might be hard to explain 100% transparent. So after clarifying the problems, we also need to define the KPI metrics to measure AI performance. Here, the KPI varies based on your problems, from precision recall of your classification problem to L2 loss for prediction problems. Besides choosing the KPI, you also need to choose a threshold to measure the progress or success of your problem definition or problem solution here. Here, different problems can lead to different thresholds. For example, for self-driving cars, the object detection accuracy needs to be very close to perfect. because a misclassification problem of a human on the road can lead to various serious accidents. After problem definition, we also need to processing the related data. We call it data processing step. As we all know, garbage in, garbage out. So this stage is very critical to the performance of AI machine learning, and normally includes four steps: data collection, which we identify the key data sources and for raw data and start to collecting your data. Data formatting, we try to convert various styles and formats of raw data to more disciplined manner for future processing. Data cleaning, here we need to handle wrong, out of data, or invalid data, or missing data here, because data is not perfect. We need to clean the data here. The last one, data sampling. Either way, you have too many or too few data. So we need to do some downsampling, trying to remove the noises, or doing some upsampling, for example, create synthetic data here if needed. After data processing, we come to feature engineering stage. Here in this stage, we try to use domain knowledge to develop relevant feature signals from existing raw data to increase the power of machine learning. For example, 10-day moving average is a very good short-term trend indicator for stock price prediction. So feature engineering is another critical stage for AI machine learning workflow because it will directly determine if you can maximize the power of AI. By the way, for more and more AI applications in the recent time, feature engineering has evolved from handcrafted features to more machine learned features, which is more scalable and effective. Okay, we come to model training evaluation stage. The most recent AI breakthrough, for example, deep learning, deep neural networks, deep reinforcement learning are happening in this stage. At this stage, engineer or data scientists will try different models from very simple linear regression to most recent deep neural networks, trying to fully consume the data we collected and feature extracted from the real life to achieve the optimal performance. Meanwhile, the loss function iteration can be also critical because depends on your roles and models and the purpose here, we try different loss function here. Besides model and loss function iteration, parameter sweeping become a very popular approach, trying for engineer to find right parameters to optimize the performance of the models. In recent years, AutoML become very popular trend to auto-select the model, loss function, and parameters for targeted problems. Though the main application for AutoML is still on structured data, which may not be applicable for autonomous vehicle yet. Okay, the last stage, which is not this stage, which is model deployment. At this stage, we try to integrate ML with existing system and try to keep it running successfully over time. Don't underestimate this stage because this stage will directly determine the real-life performance of your trained machine learning models. Normally, this stage includes deployment environment configuration, model compression, or model optimization, security and privacy compliance. Last one, monitoring the model and maintaining a model over time. Okay, we just had a quick overview of how AI workflow looks like end-to-end, right? You might be curious now to see how AI is practiced in autonomous vehicle industry. I will use Cruise as an example to see how we can use the AI in self-driving cars. As other AI machine learning problems, we start from data. At Cruise, we have an internal initiative called Continuous Learning Machine, trying to update AI models twice every week. The goal here is trying to using machine learning to automate the detection of edge cases and encountered on the real life, and setting the examples to AI driver, which is our AI models, so algorithm can self-improve. So about is the two examples here. You can see the AV encounter every day. For example, from the double parking vehicles to some white vehicle turn around, and also to the karting bikes. These are all challenging scenarios we see every day on the real life. This can help us, help the AV driver to mine various challenging scenarios on the road, so serve as a critical data sources for our model training offline. So besides raw data, a lot of signals on the road can be used for our features for AI machine learning models. For example, when human driving on the road, we always interacting with pedestrians on the road, right? Trying to predict, are they going to cross the road or not? Cruise AV can do the similar thing here. Besides the regular detection tasks, Cruise vision algorithm can consider human pulses, from which we attempt to predict the actions people may take when they cross the road. For example, if we are detecting the human are looking at their phone during the walking, we can infer that they are unlikely to cross right away or they might be distracted. So pedestrian poses can be a critical feature for us to use for better prediction and interaction. After feature engineering, we mentioned before, right? We try to updating and improve our model on a regular basis. So the high-level life cycle is like this. We try to collecting data through our on-road driving, doing a lot of feature data collection, then feeding to our model training evaluation of offline day by day, then we go into deployment. But before we do AV deployment, we test our new models in offline environment to ensure the improvements and mitigating the regressions. So how do we do the offline testing here? In Cruise, we're leveraging simulation as much as possible. So I will show a video here to see how we are using the simulation to do offline testing. So you can see we have radar, LiDAR, camera. It's trying to create even a multi-sensor environment for simulation, and we can simulate different environment here. Cool. It's a pretty cool video, huh? Of course, on-road testing is still necessary because we're trying to catch edge cases and challenging scenarios. From April this year, Cruise is partnering with San Francisco local communities to deliver foods to elderly during the COVID-19, so we can make social impact together when we're doing on-road testing. Also, as I mentioned in previous slides, COVID-19 is affecting our on-road testing a lot, and we need to be more innovative on that strategy here. So in normal scenarios, our life cycle is like this, right? We try to collecting data on the road, analyzing the data, and trying to improve the code, then doing some testing offline, then deploy again. During COVID-19, it's obvious that continuous making progress. We must need using more simulation software. Luckily, our multi-year investment in simulation have resulted in very good performance on simulation, which allowed us to continue making progress on AV performance while the majority of vehicles still off the road. Here I will show you an example for our cruise simulation. Hope you like our simulation video. As mentioned in the past videos, like our simulation framework, you can see like it can doing a lot of A/B testing without on-road testing because it can simulate in real life. Very good, but it's not that simple. There are many challenges we must overcome and some caveats we must keep in mind. For example, accuracy. So what is accuracy? Like this is a major issue between reality and simulation. So in ideal world, we want to achieve 100% accuracy in our simulation environment, but we all know it's not feasible, right? For every scenario we want to test in simulation, we have to choose how much invest in accuracy, because even some small accuracy improvement can take 100, like maybe several years to development. And here we need to sometimes using metrics, which is our software, to create a near perfect representation of a situation that AV can encounter on the road. And we measure how accurately the simulation can match reality. In some scenarios, we're also using machine learning, like deep neural networks, for example, GAN networks, to minimize the difference between the simulation data and real-time data. Here, I'll give an example here. How can we using machine learning to simulate a parallel parking? The left one is a real world example. The right one is a simulation environment. You can see they are very close to each other. Yes, parallel parking is kind of like weird scenarios on the road to detecting on the real life. Okay, so while our metric simulator can push in for 100% simulation accuracy as much as possible, it can also provide a full set of sensor inputs like LiDAR, radar, and camera for the AV system and contain various different scenarios, agents like pedestrians, vehicles, and cyclists. Combining all those segments, we can simulate very complicated on the road scenarios. For example, this one, the construction workers cross the road like a jailworker in a crowded construction zone here, right? It's very kind of a challenging scenario we're trying to solve every day. Decades of video games engines have taught us how can we simulate visual scenes using camera, but how about LiDAR and radar? They are different. LiDAR using 3D data in slices, and radar capture electromagnetic reflections, which can have the appearance of oddly shaped objects. The real challenge here is how can we find a good balance between fidelity and performance of runtime? So this is a very complex problem involving reflection in the air, reflection, ghosting, and many complexities, much more than we can discuss today. So it's still a long journey for us. Okay, as you can see, AI and machine learning is playing a critical role in cruise autonomous vehicle development. We believe with advances of AI machine learning technologies, our cruise AV will also be more intelligent and human-like to handle different scenarios on the road in both safely and comfortable manner. Thank you. I pass to Morgan.
That was so great. Thank you so much. It was so great to have you. Thank you.
Thank you, Morgan. Yeah.
Okay. If everyone could please give another warm virtual round of applause for you. Thank you, Yu. We'll see you around.
Right.
Bye. Okay, well, that was an awesome talk. I hope that you all enjoyed it. I really did. And please stick around for the next session or head over and have a one-on-one networking session, or feel free to explore the virtual booths. Hope you enjoy.